Hi everyone, welcome to Go Classes. In this lecture, we will study these two concepts: inverse relation, or I can say inverse of a relation, complementary relation, or I can say complement of a relation. The concept we will study, and then all the possible questions on these concepts we will solve. So, this is going to be a very interesting lecture because the concept we will cover maybe within the first 20 to 25 minutes we will cover the concept. Then a lot of practice we are going to do, more than 1 hour, all the possible questions we are going to solve. Okay, so let's start. Let me tell you that go classes discrete mathematics lectures, discrete mathematics compact lectures, gate PYQs, revision practice lectures, all these you can find in this playlist. On the YouTube you can search go classes discrete mathematics. In this playlist you will find all the discrete mathematics gate PYQs, compact lectures, or I can say summary lectures, revision playlist, and practice. Okay, so the link you can find in the pinned comment, also in the description, but you can search on the YouTube go classes discrete mathematics. So let's see what the content of this lecture. In this lecture we will study identity relation on a set A, the definition of identity relation. Then we will study inverse relation of a relation R. Then we will study complement of a relation. So these three concepts we will study. Then all possible practice questions we will solve. Okay, so let's start. Let's study what is identity relation. It is also called diagonal relation or equality relation. So these are different names for identity relation. So let's see what is the definition of identity relation. Let's assume we have a base set, or I can say a set A. So we have a base set A. Now, what is the definition of identity relation on set A? You can see here identity relation on set A. So we have a base set A. Now, what is identity relation on set A? Let's see the definition of that. So identity relation on set A, this we can denote by IA, that identity relation on set A, or you can simply denote by I. You can also denote by delta, okay, because it is also called diagonal relation, so you can denote by delta. It is also denoted by E because it is also called equality relation. So remember, identity relation is also called diagonal relation, it is also called equality relation. You will understand why these different names for identity relation. You will understand, don't worry. So let's see identity relation on set A. So what is that? Identity relation on set A, that is defined like this. It is basically set of all and only reflexive pairs. Okay, means this identity relation, this is set of ordered pairs of type A, where A belongs to base set A. Okay, so remember, in the identity relation we have all the reflexive pairs and only the reflexive pairs. Okay, so remember, for every element of the base set A, I can say that A, this ordered pair, will belong to identity relation, nothing else will belong to identity relation. So I can say that identity relation, this is the smallest reflexive relation. Okay, this identity relation, this is the smallest reflexive relation on base set A. Okay, so I can say that this identity relation, what this is basically smallest reflexive relation on base set A, or I can say that it contains all and only reflexive pairs. Okay, so I can say that it contains, basically it contains all and only reflexive pairs, all and only reflexive pairs. Okay, very simple, I hope you understood. For example, assume that our base set A has elements 1 to 3. Okay, 3 elements in the base set. Then what will be the identity relation on this base set A? So that will contain all and only reflexive pairs. I can say for every element in the base set, ordered pair A will belong to the identity relation. So I can say 1 1 will belong to the identity relation, 2 2 3 3. Nothing else, nothing else. Okay, and remember, If I remove 3 3, for example, if I remove 3 3, now this is not an identity relation, because you must contain all reflexive pairs and only reflexive pairs. Okay, so I hope you understood. So remember, over this base set, this is the only identity relation. Basically, if the base set is fixed, then identity relation on that base set, that is also fixed. Okay, so very simple. So identity relation contains all and only reflexive pairs. Okay, I can also say that identity relation, this is basically smallest, this is basically smallest reflexive relation, smallest reflexive relation on base set A. Okay, I hope you understood. So this is the definition of identity relation. Why it is called diagonal relation, we will see. Why it is called equality relation, see, you can easily see why it is called equality relation, because you can see in this identity relation we have ordered pairs 1 1, 2 2, 3 3. Okay, so that is the reason this is called equality relation. Why it is called diagonal relation, because you can see in the matrix representation of the relation, for relation, if I make the matrix representation, then you can see these are the diagonal elements, these are the main diagonal elements. Okay, so I hope you understood that identity relation, this is also called diagonal relation. I hope you understood the reason, and also this is called equality relation, and I hope you understood the definition. So remember, for any base set A, if the base set is fixed, then identity relation, that is also fixed. Okay, very simple. So let's see. You can see on set A, relation, what is a relation? The definition of relation we already know. Relation is subset of A cross A. So you can see R is a relation on base set A. Then what is identity relation? Identity relation is basically x comma x, these ordered pairs for all x belonging to A. Okay, so basically under identity relation, each element of the base set is related to itself and only related to itself. Okay, every element of the base set is related to itself and only related to itself. Okay, so you can see that identity relation, this is basically smallest reflexive relation on set A. Okay, so this symbol we use because identity relation, this is also called diagonal relation. So basically it contains ordered pairs A where A belongs to base set. Okay, means for every element in the base set AA, this ordered pair will belong to diagonal relation. Okay, very simple. So this is the definition. You can see diagonal relation on set A. It is also called equality relation. It is the smallest reflexive relation on A. Very simple. Now let's see, for identity relation, what will be the matrix representation, what will be the graph representation. So take any base set. You have base set A. Let's assume our base set A contains total n elements. Okay, 1 2 3 and so on, n elements. So this is our base set A. Now what will be the identity relation? Identity relation on A, on this base set A, what that will be? The definition you already know, that will be AA, that will be AA, where A belongs to the base set A. Okay, now tell me what will be the matrix representation, what will be the graph representation of identity relation. Okay, so let's see the matrix representation of identity relation. So the matrix representation that you can create in the matrix representation of any relation on set A, if you make the matrix representation, then what you will do? Then basically these elements of the base set, okay, these elements are at the header, column header and row header. So you can see it's like this 1 2 3 and so on. And okay, now you can see identity relation, what it simply means, it simply means that the main diagonal, all these elements will be 1. Okay, you can see 1 is related to 1. Okay, so it will be 1. 2 is related to 2, 3 related to 3, then and so on, n related to n. Okay, and the remaining all will be 0. The remaining all cells will be 0. All the remaining cells will be 0. Okay, so I hope you understood. So like this. So this is the matrix representation of identity relation. What will be the graph representation of identity relation? Graph representation of identity relation, very simple. In the graph representation, only self loops will be there. Okay, there is no other edge. One related to one, two related to two, three related to three, and so on. N will be related to n. That's it. Okay, all the self loop will be there, and only the self loop will be there. Okay, all and only self loops will be there. No other edge will be there. Okay, so very simple. So that's it. This is all about identity relation. It is called diagonal relation because you can see in the matrix representation the main diagonal, that is all ones. Okay, and you can see that it is also called equality relation because a is related to a for all the a in the base set. Okay, and this is the graph representation where we have all and only self loops. Okay, so that's all about identity relation. I hope you understood. Let's study the next concept, that is inverse relation. It is also called converse relation. It is also called transpose relation. So these are different names for the same concept. Inverse relation, or I can say inverse of a relation, or I can say converse of a relation, or I can say transpose of a relation. Okay. So let's see the definition. So inverse relation, it simply means inverse of a relation. Means you have a relation, then you are finding the inverse of that relation. Or I can say converse relation means you have a relation and you are finding converse of that relation. Similarly, transpose relation means you have a relation and you are finding transpose of that relation. All these are same concepts, different names for the same concept. Okay. So let's see. Let's assume we have a relation R on base set A. Let's assume we have a relation R on set A. Okay. So this relation R, for this relation R, what will be the inverse relation? So let's see what will be inverse of R. Okay, what is inverse of R? So remember, R is a relation on set A. Then what is the definition of inverse of R? Means how to define inverse relation of R. So it is denoted by R inverse. R inverse. You can also denote by RC because remember inverse relation is also called converse relation. Okay, so you can denote by RC, or you can also denote by RT, transpose relation. Okay, so remember this is how you can denote, but this is most popular, I can say R inverse. This is most popular. So inverse of R, what that will be? What will be R inverse? R inverse is very simple. R inverse will be like this. In R inverse, basically you you put ordered pairs BA such that AB belongs to R. Okay. See, understand the definition. Inverse of relation R simply means that in all the ordered pairs of R, you just swap the elements. That's it. Okay. So remember, from relation R, if you want to find the inverse of R, then what you need to do? In all the ordered pairs belonging to R, you just swap the elements. Okay, means if AB belongs to R, then you just swap the elements in this ordered pair. I can say BA will belong to R inverse. Okay, so it simply means that we are just swapping, we are just swapping, we are swapping elements in all ordered pairs, in all ordered pairs of R. Okay, that's it. This is the definition of inverse of R. Okay, so this is called inverse of R. This is also called converse of R. This is also called transpose of R. Okay, so all you have to do, just swap the elements in all the ordered pairs of R. That's it. Okay, very simple. So I can also remember, I can also write like this. For example, in R inverse, xy will belong, then it simply means that yx belongs to R. Okay, means if yx belongs to R, then xy will belong to R inverse. I hope you understood the point. Okay, very simple. So the same definition I can also write like this, that if xy belongs to R, if xy ordered pair belongs to R, then yx will belong to R inverse. Okay. So remember, you can understand like this, you can understand like this, you can understand like this. All these are same definitions. Okay. If AB belongs to R, then BA will belong to R inverse. If Yx belongs to R, then XY will belong to R inverse. If XY belongs to R, then Yx will belong to R inverse. Okay. So very simple. So the idea is very simple, that what is inverse of any relation R? Then very simple. Just swap the elements in all the ordered pairs of R. That's it. So consider this example. We have a base set containing three elements, and this is relation R defined on this base set A. Then what will be R inverse? So how to find R inverse? R inverse, that is very simple. R inverse means XY such that YX belongs to R. Okay, means if this ordered pair Yx belongs to R, then XY will belong to R inverse. Because to find R inverse, we will just swap the elements in all the ordered pairs of R. Okay, so here for this question, what will be R inverse? You just swap the elements in all the ordered pairs. So if I swap the elements in this ordered pair, then again I will get 1 1 only. Here I will get 2 2, here I will get 3 3, here I will get 2 1, here I will get 2 3. Okay, so what I will get? I will get 2 2, then I will get 3 3, then I will get 2 1, and then I will get 2 3. Okay, that's it. Very simple, right? What we are doing to find R inverse, we are swapping elements in all the ordered pairs of R. In every ordered pair, we are just swapping the elements. That's it. We will get our R inverse. Okay, very simple. So this is the definition of inverse relation for relation R. So for any relation R, how to find R inverse? Very simple. That will contain be a ordered pair such that AB belongs to R. Means you can understand like this, that if ordered pair AB belongs to R, then BA will belong to R inverse. Okay. If AB belongs to R, then BA will belong to R inverse. Very simple. Okay. So simply swap the direction of each ordered pair. Okay, for each ordered pair of R, you just swap the direction. Means you just swap the elements. This relation is also called converse. It is also called transpose. So you can see, you can call it inverse, converse, or transpose, but this is the most famous word, inverse. Let's solve this question. Suppose a relation R on a set is represented by the matrix. So this matrix representation of a relation R is given to us, and the question is asking, find matrix representation of R inverse. So from the matrix representation of R, can you find the matrix representation of R inverse? How can we find that? Think about it. If matrix representation of relation R is given to you, then how to find matrix representation of R inverse? So let's try to understand. So given matrix representation of R, find the matrix representation of R inverse. Here all you have to do, just apply the definition. Okay, so you already know, if your relation R, let's assume your relation R contains element ij, means ordered pair ij. Okay, so this is relation R which contains ordered pair ij. There can be some more ordered pairs. Okay, but this is the relation R. Then tell me, what will be the relation R inverse? If this is the relation R, then R inverse, what it will be? It will contain ji. Okay, and so on. So very simple. Now you tell me, if relation R contains ordered pair ij, then in the matrix representation of R, means in the matrix representation of R, what will happen? In the matrix representation of R, it will happen that this is the I row. Okay, let's assume this is the row I, and this is the column J. Okay, then you can see that here there will be 1. Okay, here there will be 1, because I comma j, this ordered pair, belong to R. So I can say that in the matrix representation, here you can see ij, here there will be 1. Okay, or you think like this, that you have relation R. Okay, so on one side we have relation R, on one side we have relation R inverse. Okay, so you just tell me one thing. Let's assume here you have something, some value. I am putting some value. Let's assume the value y I am putting. What this y can be, tell me, in the matrix representation of R, what this y can be? This can be either 0 or this can be 1. Okay, do you agree? This can be either 0 or it can be 1. If ij belongs to R, then y will be 1. If ij does not belong to R, then y will be 0. So y will be either 0 or 1. Okay. You tell me one thing. If ij belongs to R, then this y will be 1. Then in R inverse, what can you say? Just tell me about the matrix representation of R inverse. Matrix representation of R inverse. So in the matrix representation of R inverse, we have J here, okay, and I here. Correct? Okay, so you tell me, if y is 1, it means ij, this ordered pair I comma j belongs to R, then j comma I will belong to R inverse. So you can see, if this y is 1 in ij, then in the matrix representation of R inverse, this ji will be 1. Okay. Yes or no? This gi, this will be 1. If I put 1 in the matrix representation of R, here in ij, if I put 1, then in the matrix representation of R inverse, in the gi, I have to put 1. Okay, yes or no? Very simple point. Similarly, you tell me, if ij does not belong to R, means this ordered pair I comma j, this does not belong to R, then this y will be 0. So if ordered pair I comma j does not belong to R, then j comma I will not belong to R inverse. So this j comma I, this cell in the matrix representation of R inverse, this j comma I, this cell will be 0. Okay, so I hope you are understanding the point, that whatever ij you put here, this cell, in this cell ij, whatever you put here, that same value will go in the cell ji in the matrix representation of R inverse. Okay, I hope you got the point. I hope you understood the point. Okay, so this is the whole idea. Okay, what it means? It means that this element which is ij element, this has become ji element here. Okay, so what it is called, in a matrix, ij element has become gi element in another matrix, then this new matrix, what it will be called? It will be called transpose of this original matrix. Yes or no? So remember, I can say that this is basically transpose of the original matrix. Transpose, that's it. I hope you understood the point. Okay, so remember, we are just applying the definition, nothing else. You know, you have relation R, then what will be R inverse? R inverse will contain xy if yx belongs to R. Okay, so this concept, or I can say the definition, we have applied, and we have found out that to find the matrix representation of R inverse, we just need to take transpose of matrix representation of R. That's it. What is the reason? If anyone asks you proof, then how can you prove? Proof is very simple, remember, because you can just simply say that in this matrix representation of R, whatever this element I comma j is, this element I comma j, whatever is this element, that same element will go to j comma I in the matrix representation of R inverse. Okay, so you can see in this matrix, the ij element will become the gi element in this matrix. So I can say this new matrix, or I can say the matrix representation of R inverse, this is basically transpose of matrix representation of R. That's it. This is the simple idea. I hope you understood. Okay, so tell me, for this matrix representation of R, what will be the matrix representation of R inverse? Find matrix representation of R inverse. So I can say that matrix representation of R inverse, that will be transpose of matrix representation of R. Okay, you have matrix representation of R, you just make the transpose. So how to find the transpose of a matrix? Very simple. What you will do, every row will become column, every column will become row. Okay, so this first row will become first column. So remember, this first row, this will become first column, second row will become second column, third row will become third column. This is how you can find the transpose of a matrix. Okay, to find transpose of a matrix, first row will become first column, second row will become second column, third row will become third column. That's it. Okay, so this is the matrix representation of R inverse. I hope you understood. Let's solve this question. For two relations R1, R2, the matrix representations are given. This is the matrix representation of R1. This is the matrix representation of R2. We need to find matrix representation of R1 inverse and matrix representation of R2 inverse. So tell me, what will be matrix representation of R1 inverse? So that will be matrix representation of R1 transpose. Okay, so what you will get? The first row will become first column, second row will become second column, third row will become third column. Okay, that's it. What about matrix representation of R2 inverse? Matrix representation of R2 inverse. So that will be matrix representation of R2 transpose. Okay, so what you will get? The first row will become first column, second row will become second column, third row will become third column. Okay, that's it. I hope you understood. So now did you understand why it is called transpose relation? Inverse relation is also called transpose relation. Why? Did you understand now? The reason to call it transpose relation, because the matrix representation of R inverse is basically transpose of matrix representation of R. Okay, very simple. Now tell me the answer for graph representation. Given the graph representation of R, can you find the graph representation of R inverse? That is very simple. What you will do? You will reverse the direction of every edge in the graph. Because remember, the graph representation of R is already given to you, given the graph representation of relation R. So, in the graph representation of relation R, if you have this type of edge, A to B, means A is related to B, then in the R inverse, what will happen? B will be related to A. So, what we will do? We will just reverse the direction of every edge. Okay, that's it. So, this is the answer. Given the graph representation of R, how to find the graph representation of R inverse? We will just reverse the direction of every edge. Let me give you one example. Consider a base set A equal to ABC. This is the base set. And let's consider this relation R on this set A. And the graph representation I am giving to you. Okay, and the graph representation is like this. A is related to B, A related to A, and C is related to B. Okay, let's zoom like this. Okay, so this is the graph representation of a relation R on this set A. Okay, so tell me what will be the graph representation of R inverse? Here you can see A is related to A. So in the R inverse also A will be related to A. We are reversing the direction of every arrow. So the self loop again will become self loop. Here you can see A is related to B. So in the R inverse, B will be related to A. Okay, B will be related to A. So you can see we are reversing the direction of every edge. So here the edge is from A to B. So in the R inverse, the edge will be from B to A. And here you can see, because this is bidirectional, so you can see here you have edge from B to C. So if I reverse it, it will become C to B. Also, I have edge from C to B. If I reverse it, it will become B to C. So you can see that it will again be bidirectional. Okay, very simple. So that's it. This is how you can find the graph representation of R inverse. So to find the graph representation of R inverse, just reverse the direction of every edge in the graph representation of R. Very simple. Consider this example for a practice. So this is a relation, this is a different relation. This relation is on the base set A, B, C. This relation is on the base set X, Y, Z. Now, let's call it relation R1. Let's call it relation R2. So let's find the graph representation of R1 inverse. The graph representation of R1 inverse, what that will be? Very simple. These are the elements of the base set ABC. So what we will do? In the graph representation of R1, we will reverse the direction of every edge. So the self loop again will become self loop. Okay, from B to A and from C to A. That's it, very simple. Just reverse the direction of every edge in the graph representation of R1 to get the graph representation of R1 inverse. Okay. What about the graph representation of R2 inverse? So we have X, we have Y, we have Z. The self loops will stay self loops. Next, you can see here you have Y to Z, so it will become Z to Y. Here this is z to x, so it will become x to z. Okay, and here x to y, so it will become y to x. That's it. So this is the idea. I hope you understood. So we have seen the concept of R inverse, or I can say inverse of a relation R. So the definition is simple. Inverse of relation R, that will be yx such that xy belongs to R. Okay, means if this xy, if this ordered pair belongs to R, then yx will belong to R inverse. This is the definition. Okay, basically I can say, to find the inverse of relation R, what you do? Just swap the elements in every ordered pair belonging to R. Okay, you can see here, to get R inverse, if your graph representation, then reverse all the edges, and if your matrix representation, then you find the transpose. Okay, very simple. So that's it. This is the concept inverse of a relation. I hope you understood. Let's study the concept complementary relation, or I can say complement of a relation. If a relation is given to us, then how to find complement of that relation? So let's see the definition. So assume we have a relation R on set A. Relation R on set A. So for this relation R, how to find complement of this relation R? Or I can say, for this relation R, what will be the complementary relation? So complement of this relation R we need to find. So what will be complement of R? Complement of R. The symbol, how do we denote? We denote by R bar. Okay, we denote by R bar. So complementary relation, or I can say complement of R, we denote by R bar. Remember, we can also denote by RC. Okay, please understand here C means complement. Okay, so it will be defined in the question. Do you remember the converse relation, or I can say inverse relation, also called converse relation? That also we can denote by RC, because there C means converse. Here C means complement. Okay, so don't worry. This is the standard symbol R bar. This is the standard symbol. But if they use this symbol, then they will define that, okay, this symbol means complement of relation R. Okay, so let's see. If a relation R on set A is given to you, then how to find complement of R? Very simple. So the complement of R means R bar, that will contain all the ordered pairs which are not in R. Very simple. Basically, all the ordered pairs AB such that AB ordered pair does not belong to R. Did you understand the definition? Very simple. The name itself is telling you complement, complement, or I can say negation. Okay, so here you can see what will be complement of relation R. That will contain all the ordered pairs which do not belong to R. Means take all the ordered pairs which are not in R. That will be your complement of relation R. Very simple. I hope you understood. Okay. Remember this same thing, I can also write in another way. What I can do? Basically, this relation R, you subtract it from universal relation. Okay, what I'm saying? I am saying that, see, on this set A, what is the universal relation? Means on this set A, what is the relation containing maximum number of ordered pairs? Or I can say, on this set A, what is the largest relation possible? That is A cross A. Yes or no? Because we already know every relation on set A, that is subset of A cross A. Okay, we already know this. This concept we already know, that every relation R on set A, every relation R on set A. Okay, what we can say? We can say that R is basically subset of A cross A. And remember, every subset of A cross A is a relation on A, and every relation on A, that is subset of A cross A. So I can say that this A cross A, this is called universal relation. This is called universal relation. This is the largest relation that we can define on set A. Okay, this is universal relation. I hope you understood. So remember, every relation on set A is subset of A cross A. So there is another way I can define complement of R. What that will be? So I can say R complement will be equal to, I can say R complement, or I can say R bar, that will be basically From A cross A, you remove R. Okay, means from the universal relation, you remove all the ordered pairs which belong to R. Okay, so basically this definition again, the both are same. Okay, means in the R bar, in the complement of R, we have all the ordered pairs which are not in R. Means from the universal relation, I can say A cross A, you remove all the ordered pairs that belong to R. Okay, that's it. So you can see this is universal relation. This is a universal relation. So from the universal relation, you remove all the ordered pairs that belong to R, and then you will get R complement. I hope you understood. Okay, very simple idea. So let's see the definitions. You already know that on set A, every relation R that is subset of A cross A. Okay, on any set A, every relation R is subset of A cross A. And remember, every subset of A cross A is a relation on A. Okay, so these concepts we have already seen. So these are some special relations. We have already seen the definition of identity relation. Universal relation, what is that? Universal relation, that is basically A cross A. Okay, and empty relation, that is empty set. Very simple. So the definition of complementary relation, or I can say complement of a relation. So the complementary relation R bar is set of ordered pairs AB such that AB does not belong to R. Means to find the complement of relation R, you take all the ordered pairs which do not belong to that relation R. Consider this example. So we have this base set A containing three elements 1 to 3, and we have relation R. Then what will be R inverse? What will be R bar? Remember, this is R inverse, inverse of R, and this is R bar, this is complement of R. Understand the difference? Okay. So for R inverse, what you will do? The definition of R inverse, what that says that in R inverse we have xy, ordered pair xy, such that yx belongs to R. This is the definition. Yes or no? Means if ordered pair yx belongs to R, then xy will belong to R inverse. Okay, to find the R inverse, what we do? We just swap the elements in every ordered pair belonging to R. Okay. And what about this R bar, or I can say complement of R? In this complement of R, we have xy such that this ordered pair does not belong to R. Means you take all the ordered pairs which do not belong to R, then you will get R complement. Okay. So here you tell me what will be R inverse. So R inverse will be, to get R inverse, you just swap the elements in every ordered pair belonging to R. Okay. So it will be 1 1 2 2. You just swap the elements in the ordered pairs. 3 3. Then if I swap the elements in this ordered pair, it will become 2 1, and it will become 2 3. Okay, 2 1 2 3. That's it. And what about R bar, or I can say complement of R? So all the ordered pairs which do not belong to R, you put them in the R complement. So which ordered pairs do not belong to R? You can see 1 3 does not belong to R. So you put it in the R complement, because 1 3 does not belong to R. Okay. You can see 1 1 1 2, they belong to R. So they will not go to the R complement. So you can see 1 3 does not belong to R. So it belongs to R complement. What else? You can see 2 3. 2 3 does not belong to R. Okay. What about 2 1? Yes, 2 1 also does not belong to R. Okay. Very good. Next. What about 3 1? Yes, 3 1 also does not belong to R. What about 3 2? That belongs to R. What about 3 3? That belongs to R. Okay. So I can say this is the answer. I hope you understood. So this will be R inverse, and this will be R complement. To find R complement, you take all the ordered pairs which does not belong to R. To find R inverse, you just swap the elements in all the ordered pairs. That's it. Okay. Now we are going to solve all possible questions on inverse relation and complementary relation. So the concept we have already seen. We have seen the definition of inverse relation and the complementary relation. For any relation R, how to find the inverse relation. For any relation R, how to find complement of that relation. So the concept we have already seen. Now we will do a lot of practice, and we will see all the possible questions. on these concepts. So let's start. Let's solve this question 26 from Kenneth Rosen book exercises. The question says, let R be the relation ordered pair AB such that A is less than B on the set of integers. So the base set, that is set of integers, and this relation we are defining on integers. Find R inverse and R complement. So this is a very easy question. You can just apply the definition of R inverse, you can just apply the definition of R complement. Okay, here understand that this relation R is already given to you. The relation R is AB, these ordered pairs AB such that A is less than B. And remember, this relation R is defined on integers. Okay, so let's see. Let's find R inverse. What is the definition of R inverse? In R inverse, we just swap the elements in every ordered pair. Yes or no? Okay. Or I can say like this, that in R inverse, what we have? In R inverse, we have xy such that yx belongs to R. Correct? Okay, you can do like this. Just apply the definition. I am just applying the definition. You can see in R inverse, we have ordered pair xy such that ordered pair yx belongs to R. Means what it means? It means that if this ordered pair yx belongs to R, then xy will belong to R inverse. This is what it means. Okay. Now you just tell me what it means. Yx belongs to R. What it means? You can see AB belongs to R. It means A is less than B. So tell me yx belongs to R. What it means? It means y is less than B. Y is less than x. Okay. Do you agree with me? Notice AB belongs to R. It means that this first element is less than this second element. So yx belongs to R. It means the first element is less than second element. So y is less than x. So overall, I can say that this R inverse, what it will be? I can say R inverse will be xy such that y is less than x. Okay, do you agree with me? I am just applying the definition, nothing else. You already know this is the definition of R inverse. If yx belongs to R, then xy will belong to R inverse. Okay. Now, what it actually means, yx belonging to R. So you can see AB belongs to R. It means first element is less than second element. So yx belonging to R means this first element is less than second element. So I can say y less than x. So this same thing I can also write like this, that R inverse is equal to xy such that y is less than x. Okay. Or I can simply write it that R inverse is basically R inverse is xy such that x is greater than y. That's it. Okay, so you can see R inverse what it will be? Okay, here R inverse will be xy such that first element is greater than second element. Okay, so here if I can write like this, that R inverse will be, if I write in terms of AB instead of xy, if I use AB, then I can say R inverse will be first element greater than second element, means xy such that x greater than y. So if I replace xy with AB, then it will become AB such that A greater than B. This will be R inverse. Okay, very simple, right? Let's see how to find R complement. Just apply the definition. R complement means those ordered pairs which do not belong to R. Okay, so you can see R complement has xy such that this ordered pair xy does not belong to R. This ordered pair does not belong to R. Tell me one thing. Xy does not belong to R. What it actually means? You can see this ordered pair AB will belong to R if first element is less than second element. When can I say xy does not belong to R? Xy will not belong to R if first element is not less than second element. Yes or no? So I can say that what this actually means. This means x is first element is not less than second element. Do you agree? Okay. So I can say that R complement what it will be? It will be xy such that x is not less than y. If x is not less than y, then what can I say? Our base set is integers. If an integer is not less than another integer, then what can I say about them? If x is not less than y, then I can say that x is greater than or equal to y. Okay, that's it. This is the answer. So finally, remember what will be r bar, or I can say r complement. That will be, if I write in terms of AB, I can replace xy with AB. Then I can say that AB such that A is greater than equal to B. Okay, I hope you understood. So remember, if your relation R, that is, this is the final conclusion. Remember, if our relation R is AB such that A is less than B, if this is our relation R on integers, now you can easily see what will be R inverse. R inverse will be AB such that A greater than B. And what will be R complement? That will be AB such that A is greater than or equal to B. Okay, very simple. I hope you understood. So you can notice one thing here, that R union R inverse, if I do R union R inverse, if I do, that does not become universal relation. Okay, that does not become universal relation. Tell me here, what will be R union R inverse? In this example, what will be R union R inverse? What that will be? You can see R is AB where A less than B, and R inverse is AB where A greater than B. Means if I take the union, then I will get all the ordered pairs such that either first element is less than second element or first element greater than second element. I can say that where A is not equal to B. Yes or no? So I can say that R union R inverse, that is not A cross A. That is not universal relation. This is what I'm saying. Okay. I hope you understood. But remember, if I do R union R complement, that will definitely be A cross A, because you already know that R complement basically means A cross A minus R. Okay, yes or no? So this will always happen. Because what is R bar? What is R complement? That is A cross A minus R. So R union R inverse, that will, sorry, R union R complement will always be A cross A. But R union R inverse, R union R inverse, okay, maybe I made mistake here. You can see it should be R inverse. It should not be R complement. Okay. I am saying that R union R inverse may not be equal to universal relation, but R union R complement, that will always be equal to universal relation. Okay. You can see, if for this particular example, if I do R union R inverse, then that will be AB such that A not equal to B. But if I do R union R complement, that will be A cross A, or I can say here integers, so it means I cross I. Okay. I hope you understood this. Let's solve this question from Kenneth Rosen book. Let R be the relation AB, A divides B on set of positive integers. The base set is positive integers. Now find R inverse and find R complement. Okay, so let's see what is the relation R. First of all, the relation R is AB, ordered pair. A is related to B. That A will be related to B if and only if A divides B. Okay, if and only if A divides B. Correct? Okay, this is the symbol for divides. Divides. So very simple. Now let's see what will be R inverse and what will be R complement. Let's find R inverse. Just apply the definition of R inverse, nothing else. What is the definition of R inverse? R inverse contains ordered pair xy if yx belongs to R. Okay, or I can say that if this ordered pair yx belongs to R, then xy will belong to R inverse. Okay, so this is the definition of R inverse. Now tell me what is the meaning of ordered pair yx belongs to R. You can see ordered pair AB belongs to R. It means A divides B, means first element divides second element. So tell me what it means. Here first element divides second element. Here this simply means y divides x. Okay, yes or no? So I can say that R inverse, what that will be? That will be xy such that y divides x. Y divides x. Okay, y divides x. That's it. This is the answer. I hope you understood. In terms of AB also you can write if you want. Okay, so here you can see R inverse, what that will be. If you want to write in terms of AB instead of xy, if you want to write in terms of AB, then what you can do? You can just replace xy with AB. So here I can say this y divides x, means second element divides first element. So I can say B divides A. That's it. This is the answer. I hope you understood. Now let's find R complement. Just apply the definition, nothing else. R complement means all those ordered pairs xy such that this ordered pair does not belong to R. This ordered pair does not belong to R. Okay, you tell me what is the meaning of xy does not belong to R? Remember, AB belongs to R means A divides B, means first element divides second element. If I say xy does not belong to R, then what it will mean? It will mean that first element does not divide second element. Yes or no? I can say that it means first element does not divide second element. Okay, so finally I can say that R complement will be xy ordered pair xy such that x does not divide y. That's it. If you want to write in terms of AB, that also you can do. So R complement, what that will be? That will be AB. You can replace xy with AB. So you can see AB such that A does not divide B. Okay, A does not divide B. That's it. This is the answer. Very simple. I hope you understood. Let's solve this question from Kenneth Rosen. Let R be the relation on set of all states in the United States. So the base set is set of all states in the United States. I think 50, 52 something. Now, you can see this relation R consists of pairs A comma B. In this relation R, we have ordered pairs A comma B such that A borders state B. Okay, means A borders with state B. State A borders with state B. Now we need to find what is R inverse, what is the significance or what is the meaning of R inverse, what is the meaning of R complement. Okay, so tell me, you understood what is the relation R? Relation R is basically, relation R contains AB, ordered pair AB, where A is related to B, means state A borders state B. Okay, so you can see state A borders state B. So now tell me what will be R inverse and what will be R complement. What will be R inverse? R inverse means the definition if you apply. Okay, you can see in R, if A is related to B, then in R inverse, B will be related to A. Okay, or I can say like this, that in R inverse, I can say that xy such that yx belongs to R. Okay, just apply the definition. See, this is the definition. In every question, I am just applying the definition, nothing else. Okay, nothing complicated. I am just applying the definition. So I can say that R inverse, that means ordered pair xy such that yx belongs to R. Tell me what is the meaning of yx belongs to R? That means state y borders state x. Yes or no? I can say that state y borders state x. Tell me one thing, just a simple thing I'm asking. If state y borders state x, can I say state x borders state y? Is it symmetric? This borders, this relationship, is it symmetric? Like if this is state x, this is state y. If state x borders y, then state y borders x. Yes, correct. Okay, this is symmetric. If I'm your neighbor, then you are my neighbor, something like that. Okay, so you can see that state y borders state x. This is same as state X borders Y, borders Y. Okay. And what is the meaning of, how do I write state X borders Y? That means X related to Y. Okay. So here you can see that ultimately what I'm getting, R inverse is equal to, R inverse is basically same as R. I hope you are getting the point. Because in R inverse we have XY such that YX belongs to R. If YX belongs to R, then XY also belongs to R. Okay. If Yx belongs to R, then Xy also belongs to R because borders. This is a symmetric relation. So overall, I can say that R inverse is equal to R. Overall, I can say R inverse here. For this particular situation, I can say that R inverse will be same as R. Okay, understood? Very easy. Nothing complicated here. Okay. Let's see what about R complement. Tell me, what about R complement? R complement means AB, or I can say XY. I can take XY. XY such that this XY, this ordered pair does not belong to R. Okay. If XY does not belong to R, what it actually means? It simply means X comma Y, they do not border each other. Yes or no? Okay, I can say that X comma Y are not neighbors. That's the simple point, that X does not, X does not border Y. State X does not border state Y. Okay, that's it. So remember, this will be the R complement. R complement will be pair of those states which do not border each other, I can say. Okay, so I can say this R complement, this will be pair of those states, ordered pair, I can say pairs of states which do not border each other. Okay, that's it. This is the answer. I hope you understood. Very simple. Let's solve this question. This is a very interesting question. Total 8 questions we have, true false questions. Pause the video, try this question yourself, then see the solution. I'm going to provide the detailed solution now. Basically, true false statements we have. If R is reflexive, then can I say R inverse is reflexive? We are asking about R inverse. If R is irreflexive, then R inverse irreflexive. If R symmetric, then R inverse symmetric. If R antisymmetric, if R is transitive, partial order, equivalence relation, asymmetric. Basically, all the categories we have covered here, and we need to find what can we say about R inverse. Okay, if if information about R is given to you, then what can you say about information about R inverse? This is a very interesting question. Now let's solve it. Let's see the first statement. If R is reflexive, can I say R inverse will be definitely reflexive? Is this statement true or false? Yes, this statement is true. This statement is true. Very easily you can prove it. Let's see the proof. What is given to you? Just tell me that point. What is given to us? It is given to us that R is reflexive. Okay, R is reflexive. This is given to us, R is reflexive. If R is reflexive, then what it means? It means that in the relation R, we have all the reflexive pairs. If R is reflexive, then in the relation R, we have all the reflexive pairs. There can be some more ordered pairs which are not reflexive, but all the reflexive pairs must be there. Okay, so it's like this, that you have something like AA, BB, CC. This type of ordered pairs will be there. All the reflexive pairs will be there. For for example, let's assume that the base set is ABC. Okay, just for understanding purpose, let's assume that the base set is ABC. This is the base set. Okay, so you can see this is your relation R because R is reflexive, so it contains all the reflexive pairs. Now tell me what about R inverse now. For R inverse, what you will do? you will just swap the elements in every ordered pair. So if I swap the elements in every ordered pair, then you can see these reflexive pairs will remain as reflexive pairs. Okay, yes or no? So you can see again what we got. We got reflexive relation. So that's it. This R inverse, this is also reflexive. Okay, very simple. So this statement is true. If relation R is reflexive, then its inverse will also be reflexive. What about this statement? If R is irreflexive, then can I say R inverse definitely is irreflexive? Yes, this statement is also true. This statement is also true. For understanding purpose, let's assume our base set. You can consider base set to be 1 2 3 whatever you want to consider. For example 1 2 3 4, like that you can consider anything, you can consider any base set. So you can see what is given to you. R is irreflexive. Okay, so let's see the proof. In the proof I can say that the given information, that is the relation R, that is irreflexive. So what it means, if relation R is irreflexive, means there is no reflexive pair in R. Yes or no? In the relation R, there is no reflexive pair. If there is no reflexive pair in relation R, then if I swap the elements in the ordered pair, then also in R inverse also will not have any reflexive pair. Okay, do you agree? Or you can use the matrix representation. See what you can do, just use matrix representation. Let's use matrix representation to prove it. So you can see R is irreflexive. So in the matrix representation of R, what you will get? You will get all the diagonal elements will be 0. Okay, yes or no? All the diagonal elements will be 0. This is the matrix representation of R. Do you agree with me? Now tell me, what about the matrix representation of R inverse? That will be matrix representation of R transpose. Yes or no? I told you matrix representation of R inverse, that is matrix representation of R transpose. Okay. So you tell me, if I do the transpose of this matrix, then you can notice the main diagonal will remain same. When you do the transpose of any matrix, then the main diagonal will remain same. Okay, the main diagonal will remain same. So you can see that if this relation R is irreflexive, means the main diagonal is all 0, then you can see after transpose main diagonal is all 0. So I can say that this R inverse, that is also irreflexive. Okay, that's it. Very easy proof. Yes or no? So using matrix representation, you can easily prove it. Let's see statement 3. If R is symmetric, then can I say R inverse will be symmetric? Yes, this statement is also true. If relation R is symmetric, then R inverse, that also will be symmetric. How can I prove it? Let's see the proof. What is given to us? It's given to us that R is symmetric. Now, if R is symmetric, what can I say about R inverse? Okay, so we already know that R is symmetric. I want to check for R inverse. Okay, this is what I want to check. I want to check for R inverse. This is R inverse. And I want to check for R inverse. So, to check whether R inverse is symmetric or not, assume that AB belongs to R inverse. Okay, assume AB belongs to R inverse. Assume, or I can say let AB belongs to R inverse. Let AB belong to R inverse. So you can see, please understand, this is the given that R is symmetric. And we need to check, is R inverse symmetric or not? Okay, so you assume that this ordered pair AB belongs to R inverse. Now we need to check, can I guarantee that BA will also belong to R inverse? Correct? You just tell me a simple point. If AB belongs to R inverse, then what can you say about R? then what can you say about R? If AB belongs to R inverse, then definitely BA belongs to R. Do you agree with me? Okay. If AB belongs to R inverse, then BA will belong to R. But R is symmetric. It is given to you that R is symmetric. If R is symmetric and BA belongs to R, then I can say that AB also belongs to R. AB will also belong to R. Correct? Okay, step by step we are going. So, very simple. Now you tell me, if AB belongs to R, then what can you say about BA belonging to R inverse? Yes, if AB belongs to R, then definitely BA belongs to R inverse. Hence proved. You can see this is our starting point. We assume that AB belongs to R inverse. Now we want to check, can I say BA will belong to R inverse? Yes, I can say that if AB belongs to R inverse, if I start from here, then you can see I will I will derive that BA also belongs to R inverse. So hence proved. Okay, yes or no? That's it. So I can say that if R is symmetric, then R inverse is also symmetric. Did you understand this proof? This is a very cute proof, I can say. This is the given information, R is symmetric, and we need to check, is R inverse symmetric or not. So you start from this point, that assume that AB belongs to R inverse. Now we need to check, can I say that BA will belong to R inverse? So you just go in a step by step way. If AB belongs to R inverse, then I can say BA will belong to R. R is symmetric, so if BA belongs to R, then AB will belong to R. If AB belong to R, then BA will belong to R inverse. Okay, so I can say that if AB belong to R inverse, then BA will also belong to R inverse. So I can say that R inverse is symmetric. That's it. Very easy. Let's see this statement. Is it true or false? If R is antisymmetric, then R inverse is antisymmetric. Is it true? Yes, this statement is also true. That if the relation R is antisymmetric, then R inverse is also antisymmetric. Can we prove it? What is the given information? The given information is that R is antisymmetric. R is antisymmetric. Okay. Now, for a moment, assume that R inverse is not antisymmetric. Okay, means we can prove by contradiction. It is already given that R is antisymmetric, and what we need to prove? We need to prove that R inverse is antisymmetric. Okay. Now, for a moment, assume for contradiction, prove by contradiction. Proof by contradiction. Assume R inverse is not antisymmetric. Is not antisymmetric. Okay. For a moment, I am assuming that R inverse is not antisymmetric. Tell me, if R inverse is not antisymmetric, what it means? It means that R inverse. So I can say that R inverse will definitely contain this type of two ordered pairs xy, yx, where x comma y are different. Okay, this type of ordered pairs will definitely be there xy, yx, where x and y are different. Okay, do you agree with me? So very simple, step by step we are going. It is given that R is antisymmetric. We need to prove that R inverse is antisymmetric. So we are using proof by contradiction. I am assuming that, for a moment, I am assuming that R inverse is not antisymmetric. If R inverse is not antisymmetric, then definitely this type of two ordered pairs will be there xy, yx, where x is not equal to y. Okay, now you tell me, if this is R inverse, then what can you say about R? What can you say about relation R? You can see, if xy belongs to R inverse, then yx belongs to R. If yx belongs to R inverse, then xy belongs to R. Okay. Now, did you notice that in the relation R you have yx, xy, where x and y are different? So, did you notice this relation R? This is not antisymmetric. This is not antisymmetric. And if the relation R is not antisymmetric, then this is a contradiction. because already it is given that R is antisymmetric. Relation R, it is already given that it is antisymmetric, and you are saying that it is not antisymmetric. So there is clearly a contradiction here. Okay, there is a clear contradiction here and here. So you can see a contradiction is there. If the contradiction is there, then what the issue? The issue is our assumption is false. Okay, if the contradiction is there, it means our assumption was wrong. What was our assumption? Our assumption was that R inverse is not antisymmetric, so our assumption is wrong. So I can say that R inverse is antisymmetric. So if R is antisymmetric, then definitely R inverse is also antisymmetric. Hence proved. Okay, I hope you understood. Okay, all these proofs are very easy. If you think about it, step by step we are going. Sometimes you can use proof by contradiction, sometimes you can use matrix representation, sometimes you can use direct proof. Okay, but the point is, why we are looking at all these proofs? So that our understanding improves of all these concepts, like the definition of antisymmetric, the definition of R inverse. Okay, so that is the reason all the proofs we are seeing. So far, all the four statements, are they clear? With proof, are they clear? Let me know. Let's see statement 5. If R is asymmetric, then can I say R inverse will be asymmetric? Yes, this statement is also true. This statement is also true. We can prove it in similar way as we did for antisymmetric. Okay, similar way we can prove it. So here you can see R is asymmetric. This is given to you. Okay, this is given to you that R is asymmetric. And what we need to prove? We need to prove that R inverse will be asymmetric. See, we can actually use direct proof here. Okay, notice, if R is asymmetric, then what can you say about R? Just let me know. R is asymmetric means there are no reflexive pairs. That is one thing. Yes or no? Definitely this type of things are not there, like A related to A. This type of things will not be there. Okay, that you agree with me? Second thing, R is asymmetric, so the reflexive pairs are not there, because asymmetric relation is also irreflexive. Okay, in the asymmetric relation you cannot have reflexive pairs, so this type of reflexive pairs are not there. Okay, also, for example, if xy is there, where x is different from y, so if xy is there, then definitely yx will not be there. Okay, if xy is there, then yx will not be there. Okay, so you can see that this is your relation R. R is asymmetric, so this is how your relation R will look like. That if this happens, then this happens. If xy belongs to R, then yx will not belong to R, and this type of reflexive pairs will not be there in R. So what can you say about R inverse? You can see, to get R inverse, what you will do? You will just swap the elements in all the ordered pairs. You can see these reflexive pairs are not in R, so they will not be in R inverse also. Okay, yes or no? They will not be there in R inverse also. If the reflexive pairs are not present in R, then in R inverse also reflexive pairs will not be present. You can see, if xy belongs to R, then yx does not belong to R. So in R inverse, what will happen? In R inverse, it will happen that this, because you can see if xy belongs to R, then you can see yx will belong to R inverse. Okay, yx will belong to R inverse. And if yx does not belong to R, then xy does not belong to R inverse. Okay, so I hope you are getting the point. So you can see, just see the structure of R, because R is asymmetric. So this is how the relation R will look like. Then you can see this is how the relation R inverse will look like. And you can easily see that if this relation R is asymmetric, then relation R inverse is also asymmetric. Okay, so this is another way to prove it. Basically, we are looking at the structure of relation R, how the relation R is looking like. Then we are making a statement about the relation R inverse. Okay, I hope you understood. Very simple. Let's see statement 6. Is it true or false? if R is transitive, then R inverse is transitive. Yes, this statement is also true. Let's see the proof. Very easily you can prove it. What is given to us? That R is transitive. R is transitive. Okay. And now let's see what about R inverse. So this is R inverse. We need to check whether R inverse is transitive or not. I don't know. For a moment, assume that I don't know whether R inverse is transitive or not. It is given that R is transitive. For a moment, assume that I don't know whether R inverse will be transitive or not. Okay. I need to check whether R inverse will be transitive or not. I need to check. So, what you do? If you want to check R inverse is transitive or not, then what you will do? You will assume that A is related to B in R inverse and B related to C in R inverse. Okay. A related to B, B related to C in R inverse. Now we want to check, can we guarantee that A will be related to C in R inverse? Is there a guarantee that A will be related to C in R inverse? Is there a guarantee? Can you guarantee this? This is the question mark. Okay, you are assuming that A related to B in R inverse, B related to C in R inverse. Can you guarantee that A will be related to C in R inverse? So this is what we have. Okay, now from here, this is the relation R. So you can see, if AB belongs to R inverse, then BA belongs to R. If BC belongs to R inverse, then CB belongs to R. Okay, do you agree? And remember, R is already transitive. So in relation R, you can see C related to B, B related to A in the relation R. Then because this R is already transitive, so C will be related to A. Okay, so here I can say that, from here I can say that, from here we can say that C will be related to A. C will be related to A in R. If C is related to A in R, then I can say A will be related to C in R inverse. A will be related to C in R inverse. Okay, that's it. This is what we wanted to prove. Yes or no? So you can see that R inverse is also transitive, because you are starting from here. You are assuming that A related to B in R inverse, B related to C in R inverse. Now, then here we are coming. We are coming here that AC related to R inverse. Okay, you can see A related to C in R inverse. So you can see that R inverse is also transitive, hence proved. Very simple. This is a cute proof. I hope you understood. Let's see this statement. If R is partial order, then can I say R inverse is partial order? Yes, this statement is also true. This statement is also true. Actually, there is nothing to prove here, because what is partial order? When can I say R is partial order? Remember, partial order means three properties are there. What are the three properties? Reflexive. If relation R is partial order, it simply means it is reflexive and it is antisymmetric and it is a transitive. Okay. If a relation has all these three properties, then it means it is a partial order. So remember, these three properties, if these are satisfied, all these three properties are satisfied by relation R, then R is partial order. Okay. So this is the definition of partial order. Now we have already seen, if R is reflexive, then R inverse will be reflexive. If R is antisymmetric, R inverse will be antisymmetric. If R is transitive, then R inverse will be transitive. This we have already seen. Okay, this we have already seen that if I take the inverse, this is your relation R. R is reflexive and antisymmetric and transitive. Now you can easily see that if I do the inverse of reflexive, it again will be reflexive. If I do the inverse, then remember, reflexive property is preserved by the inverse. Antisymmetric property is also preserved by inverse. Transitive property is also preserved by inverse. Correct? So you can see that what we got. Basically, you are taking the inverse, and again, you got reflexive, antisymmetric, transitive properties you got. So I can say that R inverse, this is also partial order. That's it. This is very easy proof. We have already seen that reflexive property is preserved by inverse, antisymmetric property is preserved by inverse, transitive property is preserved by inverse. So for this relation R, if I take the inverse, then you can see I will again get partial order relation. Very simple. Let's see this statement. If R is equivalence relation, then can I say R inverse will be equivalence relation? Yes, this statement is also true. And there is nothing to prove here because notice what are the definition of equivalence relation. If R is equivalence relation, what it means? It means this relation R is reflexive and symmetric and transitive. This is the definition of equivalence relation. If a relation is reflexive and symmetric and transitive, if all these three properties are satisfied by a relation, then that relation will be called equivalence relation. And we have already seen that the reflexive property is preserved by inverse, symmetric property preserved by inverse, transitive property preserved by inverse. So if I take the inverse of R, then again I will get equivalence relation. Okay, so you can see that by inverse, if I take the inverse, if I take the inverse of relation R, then these properties will be preserved. Okay, I will get reflexive and symmetric and transitive. Okay, so you can see the R inverse that I'm getting, that is also equivalence relation. Hence proved. That's it. So that's it. I hope you understood. So this is the conclusion. These 8 statements we have seen with proof. Did you understand? You can see R is reflexive if and only if R inverse is reflexive. Means the inverse, it preserves reflexive properties, it preserves irreflexive property, it preserves symmetric property, it preserves antisymmetric property, it preserves asymmetric property, it preserves transitive property, it preserves partial order property, it preserves equivalence relation property. Very interesting, right? Yes or no? When you take inverse of a relation, then all these properties are preserved. R is reflexive if and only if R inverse is reflexive. R is irreflexive if and only if R inverse is irreflexive. R is symmetric if and only if R inverse is symmetric. R is antisymmetric if and only if R inverse is antisymmetric. R is asymmetric if and only if R inverse is asymmetric. R is transitive if and only if R inverse is transitive. R is partial order if and only if R inverse is partial order. R is equivalence relation if and only if R inverse is equivalence relation. All these properties, they are preserved by inverse. Very simple, very interesting. I hope you understood. So in this question, you can see we have done this one, this one, this one, this one. You can see if R is reflexive, then R inverse will be reflexive. If R is symmetric, then R inverse will be symmetric. If R is transitive, then R inverse will be transitive. If R is antisymmetric, then R inverse will be antisymmetric. So these we have done. What about this first one? If R is a relation on set A, then can I say R union R inverse will be symmetric? Let's see. This is the question. This is the part A, that you have a relation R. You have a relation R on set A. Okay. Now tell me, what can you say about R union R inverse? What can you say about this? R union R inverse. Can I say it will be symmetric? Prove that R union R inverse will be symmetric. Okay. So if you have a relation R on A, then what you need to do, you need to prove that R union R inverse is symmetric. This is what we need to prove. So it's very easy to prove. What will be the starting point to prove whether a relation is symmetric or not? We have done a lot of practice. For any relation, if I want to prove it is symmetric or not, then what is the starting point? You assume that a comma b ordered pair belongs to this relation, then you check ba belongs to this relation or not, yes or no. Okay, so let's assume that a comma b, this ordered pair belongs to r union r inverse, correct? Okay, so you tell me, if this ordered pair belongs to r union r inverse, then there are two cases. What are the two cases? Case 1, just tell me what are the two cases. Case 1 is that this AB belongs to R. There is case 2 also. Case 2 is this AB belongs to R inverse. Okay, because if this ordered pair AB belongs to R union R inverse, then maybe this AB belongs to R, or maybe this AB belongs to R inverse. These are the two cases. Now you notice, if AB belongs to R, then if AB belongs to R, then definitely BA belongs to R inverse. Okay, agree? If AB belongs to R, then BA will belong to R inverse. Okay. Now you notice, AB belongs to R, BA belongs to R inverse. Then can I say BA will belong to R union R inverse? Yes. If BA belongs to R inverse, then BA will also belong to R union R inverse. That's it. So you can see in this case 1, you can notice BA belongs to R union R inverse. What about case 2? In case 2, AB belongs to R inverse. So if AB belongs to R inverse, then BA will belong to R. Yes or no? If AB belongs to R inverse, then BA will belong to R. Now notice BA belongs to R. If BA belongs to R, then BA also belongs to R union R inverse. So you can see whatever case you take, case 1 or case 2, you can easily see in both the cases you can see that BA belongs to R union R inverse. So if AB belongs to R union R inverse, then BA also belongs to R union R inverse. So that's it. Okay. So I can say that R union R inverse is a symmetric. Okay, hence proved. That's it. Very simple proof. Remember, to check whether any relation is symmetric or not, this is always the starting point. We always assume that AB belongs to that relation, then we check, can I say that BA also belongs to that relation? Okay, so we are just using the same template, nothing else. Nothing fancy. We are just using the basic proofs, nothing else. Okay, I hope you understood this one. Let's solve question 51 from Kenneth Rosen book. Show that the relation R on set A is symmetric if and only if R equal to R inverse. This is what we need to prove. In this question, actually, there are two sides because the question is asking us to prove if and only if. Understand this. If and only if. Okay. I told you one thing, that whenever you need to prove P if and only if Q, P if and only P if and only if Q. Okay, whenever this type of statement we need to prove, this type of statement basically has two sides. What are the two sides? One side is if, and another side is only if. Okay, basically this statement has two sides, or I can say this statement I can write like this, that there is P if Q and there is P only if Q. Okay, do you agree? You can see there is P if Q and there is P only if Q. Okay, so you can see P if Q and P only if Q. P if Q, this you can understand, this is same as Q implies P. Means you assume, means Q is given and then we need to prove P. Okay, please understand P if Q. So here Q is given and we need to prove P, because P if Q I can write like this, Q implies P, and P only if Q I can write it P implies Q, means P is given and we need to prove Q. Okay, I hope you understood. So in this question also we need to prove two sides. The one side is that if you have symmetric relation that is given, then we need to prove that R equal to R inverse. And the second side is, if R equal to R inverse is given, then we need to prove that it is symmetric relation. So these are the two sides. I hope you understood. Okay, so remember, in this question there are two sides. If and only if there are two sides. So what we need to prove? We need to prove there are two things that we need to prove. The first thing is that given R symmetric, given R symmetric, then okay, given R symmetric, then prove R equal to R inverse. This is one thing that we need to prove. And what is the second thing that we need to prove? In the second thing, it is given that R equal to R inverse. And then we need to prove that R is symmetric. Okay, I hope you understood. So these two things we need to prove, first and second. Because this statement, remember this question number 51, this has if and only if. We need to prove if and only if. So there are two directions. We need to prove both the directions. Means if it is given that R is symmetric, then we need to prove R equal to R inverse. And another direction is, if it is given R equal to R inverse, then we need to prove that R is symmetric. Okay, so both these, let's prove one by one. Okay, so let's see the first one. The first one is, what is given to us? R is symmetric, this is given to us. R is symmetric, this is given to us. And what we need to prove? We need to prove that R is equal to R inverse. R is same as R inverse. Okay, now there are multiple ways to prove it. Let me use method one, that is matrix representation. Tell me, for a symmetric relation, the matrix also will be symmetric, yes or no? Okay, so you can see proof one. Let's see the proof one, that is use matrix representation. Use matrix representation. How to use matrix representation? You can see that R is symmetric. Okay, so it's already given that R is symmetric. If a relation is symmetric, then its matrix also will be symmetric. Okay, yes or no? Then its matrix also will be symmetric. For a symmetric relation, the matrix also will be symmetric. So you tell me, if a matrix is symmetric, then its transpose will be same as this matrix. Yes or no? So if matrix is symmetric, then I can say that this matrix will be same as its transpose. Okay, and you already know the transpose of matrix of R, that is same as matrix of R inverse. So you can see that matrix of R is same as matrix of R inverse. Okay, means I can say that matrix of R, that is same as matrix of R inverse. Matrix of R is same as matrix of R inverse. What it means? It means R is same as R inverse. Okay, is this clear? It means R is same as R inverse. Very easy proof. Did you like it? I think very easy. Okay, using matrix representation very easily you can prove, because R is symmetric, so the matrix will be symmetric, and for symmetric matrix the transpose will be same as the matrix. And you already know the transpose of matrix of R, that is same as matrix of R inverse. So matrix of R, matrix of R inverse, they are same. So R is same as R inverse. This is the proof one. Of course, the proof two also we can use if you don't want to use matrix representation. Okay, then also we can prove, there is no problem. Let me prove it without matrix representation also we can prove. So let's see proof two. So it is given that R is symmetric, and we need to prove that R is equal to R inverse. See, when we need to prove that two set are equal, then what actually we will do? Notice, to prove, to show set A is equal to set B, tell me what we do? if I want to show that set A is equal to set B, what we do? The first thing is we show that if X belongs to A, then X belongs to B. If X belongs to A, then X belongs to B. The second thing we prove is if X belongs to B, then X belongs to A. Yes or no? Do you agree? In the set theory, we have already seen this type of proofs. If you want to prove that set A is equal to set B, then this is what you need to do. Okay. Take any element in A, then you prove that it will belong to B. Take any element in B, then you prove that it belong to A. Okay, very simple. So the same thing we are going to do here. It is given that R is symmetric, and I need to prove that R is equal to R inverse. So what you do? First, I will prove that every element of R belongs to R inverse. Then I will prove that every element of R inverse belong to R. Okay, yes or no? So you can see first I will prove that R is subset of R inverse. Means every element that belongs to R, that will also belong to R inverse. Okay. Okay, so I can say first thing I will prove is let AB belong to R. Okay. Means assume some element belong to R. Now I need to prove that this element will also belong to R inverse. Okay. Now if AB belong to R, then because R is symmetric, okay, then because of symmetric property, R symmetric. Because R is symmetric, so I can say that BA also belong to R. BA also belong to R. If BA belong to R, notice, if BA belong to R, then definitely AB will belong to R inverse. AB will belong to R inverse. That's it. This is what we wanted to do. We started from AB belonging to R. Now we have proven that AB will also belong to R inverse. Okay, that's it. So you can see this thing we have done. Now let's do the second thing. Let's assume that AB belongs to R inverse. Let's assume AB belongs to R inverse. Then tell me, if AB belongs to R inverse, then BA will belong to R. Then BA will belong to R. Now notice, R is symmetric. This is given to you that R is symmetric. Okay, it is already given to you that R is symmetric. So if BA belong to R and R is symmetric, then AB also belong to R. That's it. This is what we wanted to prove, that if AB belong to R inverse, then AB will belong to R. If AB belong to R, then AB belong to R inverse. So you can see this is what we have done. If element belong to A, then element belong to B. If element belong to B, then element belong to A. So I can say that set A and set B are same. So I can say that R is same as R inverse. That's it. This is the proof too. Another cute proof. I hope you are loving all these proofs. They definitely will improve your analytical skills, your problem solving skills, your intuition. Are you loving these proofs? Are you understanding these proofs? Let me know. These are simple, cute proofs. Step by step, we are going, nothing else. And I'm also telling you all the context. See, everything I'm writing, nothing I'm skipping. From the previous lectures, if something we need, then I'm writing so that you can understand it very clearly. Okay, all these are very beautiful proofs, cute proofs. Okay, so that's it. You can see this is the proof 2 for this one. And what we wanted to do, so remember this first one we have done, means if the relation is given to you as symmetric, then we need to prove R equal to R inverse. This is what we have done. This we have done. And for this, I have given you 2 proof. Now let's see the second one, means if it is given that R equal to R inverse, then can you prove that R will be symmetric? Okay, now the second is, it is given that R equal to R inverse. This is given to you. And what we need to show, what we need to prove? We need to prove that R is symmetric. Tell me one thing. I told you in the previous lectures to show if some if some relation. In the previous lectures, we have already seen that to check whether a relation is symmetric or not, what is the starting point? To check if some relation is symmetric or not. The starting point will be, you assume a comma b belonging to R, and then you find out, can you guarantee that BA will belong to R or not? Yes or no? So I want to prove that R is symmetric. So what will be the starting point? Tell me. So the starting point will be, let AB belong to R. Okay, do you agree? In the previous lectures, we have already seen that to check whether any relation is symmetric or not, the starting point is let AB belong to R. Now, can you guarantee that BA will also belong to R? That is the question. Okay, so you can see, let AB belong to R. Now, if AB belong to R, then what can I say? AB belongs to R, then definitely BA belongs to R inverse. By the definition of inverse, if A related to B in R, then B will be related to A in R inverse by the definition of inverse. Okay, we are using the definition of inverse here. Also notice R and R inverse are same, because R inverse, okay, see here we are using the definition of inverse. And notice that R and R inverse are same. What it means? Because already it is given that R is same as R inverse. It means that AB belongs to R inverse also. AB belongs to R inverse also. And remember, from here also, because R and R inverse are given to you as same, R and R inverse, they are both same. So I can say that BA belongs to R also. Okay, is this clear? Now from this you can see, if AB belongs to R, this was our starting point, and we have proven that BA will also belong to R. That's it. So R is symmetric. Okay, yes or no? From these two, okay, from these two, that's it. So R is symmetric. Hence proved. That's it. Very cute proof. So finally, this question number 51 from the Kenneth Rosen book we have done. Okay, we have completed. I hope you understood. See, step by step, I'm telling you everything. If you have if and only if statement, then that is basically that is made of two statements. So you need to prove both these statements. Okay. So you can see in this question number 51, these two statements we need to prove. For the first statement, we have seen two proof. For the second statement, also we have seen one proof. So overall, this question 51 we have completed. Okay, I hope you understood. Let's solve question 52 from Kenneth Rosen book. Show that the relation R on a set A is antisymmetric if and only if R intersection R inverse is subset of diagonal relation. Again, this statement is if and only if statement. Notice, this statement is again if and only if statement. What I told you about if and only if statement, it is made of two statements. Okay, what are the two statements? Because this is if and only if statement, so here actually we need to prove total two statements, 1 and 2. What is the first statement that we need to prove? The first statement we need to prove is, if A is antisymmetric, given A antisymmetric, if R is antisymmetric, given R is antisymmetric, A is the base set, R is the relation, given R is antisymmetric, what we need to prove? Then prove that R intersection R inverse, R intersection with R inverse, this is subset of identity relation, or I can say diagonal relation. Okay, this is the first statement that we need to prove. And what is the second statement that we need to prove? The second statement we need to prove is, given that R intersection R inverse is subset of diagonal relation, then means if this is given, then we need to prove that R will be antisymmetric. Then we need to prove that R will be antisymmetric. Okay, pause the video, try this question yourself, both the parts, part 1, part 2, and then you play the video. Okay, now let me prove the part 1, then we will prove the part 2. So let's see the part 1. In the part 1, what is given to us? It is given that R is antisymmetric relation. And what we need to prove? What we need to prove? We need to prove that R intersection R inverse, this will be a subset of, this will be a subset of diagonal relation. Okay, so this is the first part that we need to prove. Okay, so you can see R is antisymmetric, this is given to you. And what can you say about R intersection R inverse? Tell me one thing, if R is antisymmetric, then how the R will look like? What will be the structure of R? Tell me, if R is antisymmetric, then what will be the structure of R? You can see R will look something like this because R is antisymmetric. So in R, you can have some ordered, some reflexive pairs, right? Reflexive pairs are allowed, but not necessary. Maybe A belongs, maybe BB does not belong. Okay, do you agree? Because R is antisymmetric. So in antisymmetric relation, reflexive pairs are allowed, but it's not necessary. Means reflexive pairs might be possible, might exist, or may not exist. Okay. So you can see I'm just telling you the structure of R, how the relation R will look like. The relation R can have some reflexive pairs, it can have, or maybe there is no reflexive pair, or maybe there are all the reflexive pairs. The point is reflexive pairs are allowed. They can exist in the antisymmetric relation. Okay. Also, you notice, because R is antisymmetric, so if I have, for example, x y, if I have x y, if I have x y, then definitely y x will not be there, so that x and y are different. Okay, let x and y be different. Okay, so you can see that if this is there, then this will not be there. Okay, so this is how your relation R will look like, because R is antisymmetric. So our antisymmetric relation looks something like this. Now you tell me, what about R inverse? What about R inverse? You can see in R inverse, what you will do? You will just swap the elements in all the ordered pairs. So R inverse will also have A. Okay. R inverse won't have BB, because if BB does not belong to R, then R inverse also does not have BB. Okay. If XY belongs to R, then YX belongs to R inverse. Okay. And if YX does not belong to R, then I can say XY does not belong to R inverse. Okay. Now you tell me what their intersection will look like. R intersection R inverse, what it will look like. Notice one thing, R intersection R inverse, what it will look like. If there is a ordered pair, if there is a reflexive pair, if there is a reflexive pair in R, then that reflexive pair will also be there in R inverse. So that reflexive pair will be there in R intersection R inverse. Are you getting my point? If some reflexive pairs belong to R, then those reflexive pairs will also belong to R inverse. So they will also belong to intersection. If some reflexive pair does not belong to R, then it will also not belong to R inverse. So it will not belong to intersection. Okay. But here you notice one thing. If XY, where X and Y are different, if XY belong to R, then XY does not belong to R inverse. Did you notice? If XY belong to R, then XY does not belong to R inverse. If YX belong to R inverse, then YX does not belong to R. So in the intersection, we won't have any of these. Okay. So finally, did you understand that this intersection R inverse? Did you notice this is subset of delta? This is subset of diagonal relation. I hope you understood. Okay. So I hope you understood the proof. This is basically intuition. Is this clear to everyone? Okay. Let me just give you another proof. Okay, which will feel more formal. Okay. But I hope you understood this, that we are proving using the structure of R, because R is antisymmetric. So using the structure of R, we are proving it. I hope you understood. But the point is, let me just quickly tell you another formal proof, or I can say proof 2. Okay, just quickly let me prove it. You can see what we need to prove. We need to prove that R intersection R inverse is subset of diagonal relation. And if R intersection R inverse is subset of diagonal relation, what it actually tells you? It tells you that R intersection R inverse cannot have this type of ordered pair where x comma y, where x and y are different. Okay, please understand what this actually means. Please understand what this means. This simply means that what it actually means. It means that this type of ordered pair x y, this type of ordered pair will never belong to R intersection R inverse where x and y are different. Okay, where x and y are different, this type of ordered pairs x comma y, where x comma y are different, this type of ordered pairs will never belong to R intersection R inverse. Okay, also remember the reflexive pair may or may not belong to R intersection R inverse, because if reflexive pair belongs to R, then that reflexive pair will also belong to R inverse, so it will belong to R intersection R inverse. And if a reflexive pair does not belong to R, then it will not belong to R inverse also, so it will not belong to intersection also. Okay, so basically this is what we need to prove, that if R is antisymmetric, then if x and y are different, then this type of ordered pair x comma y will never belong to R intersection R inverse. Okay, so let's use proof by contradiction. Okay, let's use by contradiction. Let's prove by contradiction. For a moment, assume that x comma y, this type of ordered pair belongs to R intersection R inverse. Okay, just assume this, that x comma y, this ordered pair belongs to R intersection R inverse. Now, if this ordered pair belongs to R intersection R inverse, this element belongs to intersection. What it means? What it means? It means that this element belongs to R and this element belongs to R inverse. Correct? Okay, because this element, remember, this element belongs to intersection. So this element belongs to R and this element also belongs to R inverse. If an element belongs to intersection, it means it is common in both of them. Okay, so now notice one thing. Xy belong to R. Then what can I say? Or from here, look at this. Xy belong to R inverse. Then from here, what you can say? If xy belong to R inverse, then by the definition of inverse, you can see that yx will belong to R. Okay, now there is a problem. Xy belong to R, yx belong to R, and x and y are different. So there is a contradiction. Why? What is the contradiction? Because from here you can see, that from this and from this, from here you can see that R is not antisymmetric. Yes or no? Do you agree? Because xy belong to R, yx also belong to R, where x and y are different. So R is not antisymmetric, but it is given that R is antisymmetric. So there is a contradiction. Yes or no? So you can see there is a contradiction here. You can see there is a contradiction here. There is a contradiction here. So because there is a contradiction here, it means our assumption is wrong. Okay. So our assumption is wrong. What it means? It means that this type of pair cannot belong to R intersection R inverse. Okay. And that is what we wanted to prove. I hope you understood. Don't worry if you did not understand this one. This idea, if you did not understand, then you can understand this idea. Okay. This idea, also this idea, if you combine them, easily you can understand what this question 52 is saying. I hope it is clear. Okay. Let's move on. Let's see the second direction, because remember this first direction we have proven. This is what we have proven, but this second direction also we need to prove, that if R intersection R inverse is subset of identity relation, then R is antisymmetric. Okay, so this is the second side we need to prove, that it is given that R intersection R inverse is subset of identity relation. And what we need to prove? We need to prove that R is antisymmetric. R is antisymmetric. This is what we need to prove. So let's do. Let me show you a very cute proof for this. Just use the definition of antisymmetric relation. What is the definition of antisymmetric relation? Do you remember? Antisymmetric relation definition. Antisymmetric relation. Just use the definition of antisymmetric relation. If you remember, I told you that if you have a relation R on set A is antisymmetric, if and only if whenever A comma B belong to R and B comma A belong to R, then you can see whenever I can say whenever so this is the definition of antisymmetric relation. In the lectures we have already seen this, that a relation R on set A is antisymmetric if and only if whenever AB belong to R and BA belong to R, then A equal to B. Okay, do you agree with me? Do you remember this definition? Let me know. If AB belong to R and BA belong to R, then A equal to B. So just use this definition of antisymmetric relation and you can easily prove it. Okay, so you can see it is given that R intersection R inverse, that is subset of identity relation. We need to prove that R is antisymmetric. To prove that R is antisymmetric, let's start with let AB belong to R. Okay, AB belong to R and BA belong to R. Okay, so you can see we are assuming that AB and BA they both belong to R. Now we need to prove that A will be equal to B. This is what we need to prove. Please understand, this is given that R intersection R inverse is a subset of identity relation. This is given. Okay, now forget about it. We need to prove that R is antisymmetric. To prove R is antisymmetric, I will start with this, that AB belong to R and BA belong to R. Now I need to prove that A will be equal to B. From here, if I can prove that A equal to B, then it means R is antisymmetric. Okay, so you can see from here what I can say. I can just use the definition of inverse. Just use the definition of inverse. If AB belong to R, then BA will belong to R inverse. If BA belong to R, then AB will belong to R inverse. Do you agree? Now you notice AB belong to R also, AB belong to R inverse also. BA belong to R also, BA belong to R inverse also. Now you take these two. AB belong to R, AB belong to R inverse. So from these two, what I can say? Okay, from these two, what I can say? Means AB is common in R comma R inverse. Okay, from these two. This element belongs to R also, this element belongs to R inverse also. So I can say that this element belongs to R intersection R inverse. Yes or no? If this element, same element AB, if this belongs to both R comma R inverse, then it will also belong to their intersection. Yes or no? So this is the point, that AB belongs to R intersection R inverse. But already it is given that R intersection R inverse is subset of identity relation. This R intersection R inverse, this is subset of identity relation. Okay, this is subset of identity relation. What it means? It means that this AB, this belongs to identity relation. Okay, yes or no? Because R intersection R inverse, this is subset of identity relation. So I can say that this AB actually belongs to identity relation. AB belongs to identity relation. But in the identity relation, we only have reflexive pairs. In the identity relation, we only have all and only reflexive pairs. So it simply means that A is equal to B. Hence proved. I hope you loved this cute proof. This is really the cute proof, because here in this particular proof, we are just using the definition of antisymmetric relation. Antisymmetric relation definition is very simple. A relation on a set is antisymmetric if and only if these two things happen, means AB belong to R and BA belong to R, then A equal to B. So you start from this, means you assume that AB, BA, they both belong to R. Then you need to prove that A equal to B. If you can guarantee that A equal to B, then it means it is a antisymmetric relation. Okay, and you can see this is what we have proven. We start from here and we have proven that we have given the guarantee that A will be equal to B, so it is antisymmetric relation. Okay, this is what we wanted to prove, that R is antisymmetric. So that's it. So you can see this direction also we have proven, this direction also we have proven. So this question 52 is done. We have completed it. Okay, very simple. Let's solve question 53 from the Kenneth Rosen book. Show that the relation R on a set A is reflexive if and only if the inverse is reflexive. This question we have already done. Okay, this question in this lecture we have already done. If you remember, we have proven that if R is reflexive, then R inverse will be reflexive. This question actually we have already completed. We have already proven that if relation R is reflexive, then R inverse is reflexive. And remember one more thing, that R inverse whole inverse, if you do, that will be R. Okay, if R inverse whole inverse, if you do, that will be R. So basically both the directions easily you can prove. Okay, is this clear? Means for a moment if you assume this is S, then this will be S inverse. Okay, are you getting my point? R inverse whole inverse, that is same as R. So this direction we have already proven. Now how to prove this other direction? How to prove this other direction? See, if you want to prove this direction, like if R inverse is reflexive, then how will you prove that R is reflexive? If you want to go in this direction, then let me tell you how to do this. Very easy. For a moment you assume this S, then this will become S inverse. And now this, what it has become, if S is reflexive, then S inverse is reflexive. This we have already proven. If R is reflexive, then R inverse is reflexive, we have proven. If S is reflexive, then S inverse also will be reflexive. Okay, I hope you understood. So you can see both the directions you can easily prove. Is this clear? So this question 53 we have already completed in this lecture. We have already seen this proof that inverse of a reflexive relation is reflexive. Okay, let's solve question 54 from Kenneth Rosen book. Show that the relation R on set A is reflexive if and only if the complementary relation is irreflexive. This question is about complementary relation, not about inverse relation. And this is another very easy question. Here you can see what we need to prove. Basically, again, this is if and only if statement. If and only if. Okay, so there are two sides here. What are the two sides? The first side is given R is reflexive. Given R is reflexive, we need to prove that R complement irreflexive. Okay, this is what we need to prove. And what is the second side? The second side is given R complement irreflexive, means it is given that R complement is irreflexive, then we need to prove that R is reflexive. Okay, both the sides we need to prove, and it's actually very easy. Here, this is the complement relation, so it's actually very easy. So let's see the first side. The first side is what is given to us. It's given that R is reflexive. Okay, and what we need to prove? We need to prove that R complement is irreflexive. Notice one thing, reflexive means it contains all the reflexive pairs. Irreflexive means it does not contain any reflexive pair. Okay, yes or no? So here actually you can very easily use the matrix representation. Okay, so the proof is actually very simple. Just use the matrix representation. just use matrix representation. Okay, so let's use the matrix representation. You can see it is given that R is reflexive. So how the matrix of R will look like? Tell me how the matrix representation of R will look like. If R is reflexive, then in the matrix representation of R, all the diagonal elements will be 1. Correct? Agree? Very simple. Okay, the remaining can be anything, but the point is the diagonal elements will be all 1. Now you tell me what will be the matrix representation of R complement? R complement means all the 1 will become 0, all the 0 will become 1. Yes or no? Okay, so tell me what will be the matrix representation of R complement? Matrix representation of R complement. Remember the definition of R complement, you understand? R complement means all those ordered pairs which do not belong to R. All those ordered pairs AB such that AB does not belong to R. Means if something belong to R, it will not belong to R complement. If something does not belong to R, it will belong to R complement. Okay, yes or no? So, okay, I hope you understood. So you can see that if this is the matrix representation of R, then what will be the matrix representation of R complement? All the ones will become 0, all the zeros will become 1. Okay, yes or no? So the man diagonal will become 0. Okay, the man diagonal will become 0. So you can see that if the man diagonal is all ones, then it simply means R is reflexive. Okay, and here you can see if man diagonal is all 0, it means R complement is irreflexive. Okay, that's it. Hence proved. So just using the matrix representation, very easily you can prove it. Okay. Another way is you can see if R is reflexive, it means it contains all the reflexive pairs. So in the R complement, there will be no reflexive pair. Very easy. You don't even have to do anything. Just visualize in your mind. Just think in your mind. If R is reflexive, it means R contains all the reflexive pairs. So in the R complement, these reflexive pairs will not be there. R complement will not contain any reflexive pair. So it is irreflexive. Okay, very simple. Now, what about the second direction? In the second direction, it is given that R complement is irreflexive. R complement is irreflexive. And we need to prove that R is reflexive. We need to prove that R is reflexive. Again, you can use the matrix representation. Or if you don't want to use the matrix representation, then just think in your mind. Okay, just use the definition of complement. You can see if R complement is irreflexive, means R complement has no reflexive pair. So if I take the complement, then it will contain all the reflexive pairs. Yes or no? Very simple point. Okay, or you can think like this, that R complement, again complement will be R. Okay, very simple. Very simple point. If I do R complement, then again complement, it will be same as R. So you can see that if R complement is irreflexive, means it does not contain any reflexive pair, then all the reflexive pairs will belong to R. Okay, are you getting my point? Very simple. So just use the definition, nothing else. Okay, hence proved very easily. That's it. So that's it, everyone. In this lecture, we have we have studied inverse relation, complement relation, complementary relation, or I can say complement of a relation. These concepts we have studied, and all the possible questions from various standard resources from Kenneth Rosen I have taken. We have done the complete analysis. We have seen the proof. For some questions, we have seen multiple proof. So intuition, proof, concept, examples, everything we have done in this lecture for these two concepts: inverse relation and complementary relation. Okay, everything has been done. All the questions that I could found in the standard resources, I have taken them, and we have solved them. Okay, so thank you, everyone. Please like this session. Please put your comment and let me know your feedback of this lecture. Did you understand everything? Did you love this session? Did you love the proofs? Okay, so let me know in the comments. Okay, thank you everyone.